Every electronic device you've ever used has one purpose: converting energy into something useful. In this lecture, we'll uncover how batteries provide electrons of energy, discover where this energy goes in series circuits, and determine how much of this energy is actually useful for us. By the end, you'll know how to calculate the work done, power, and efficiency in basic series circuits. In the last lecture, we discussed in more detail what is going on in a series circuit consisting of a battery and a resistor. We looked at current on the microscopic scale and introduced the electrical resistance, which determines how fast current can flow through a circuit for a given battery voltage. There's one more key property of circuits that we haven't discussed, however, which is the energy. Now, back in lecture 4, we already introduced the change in electrical potential energy as the test charge times the potential difference. In our simple circuit, as an electron goes from the negative terminal of the battery to the positive, we know it is experiencing a potential difference due to the battery. The potential difference is positive because the electron goes from the negative terminal to the positive. So the change in potential energy is simply the charge Q times V, which is minus E times V for one electron. By the way, I'm aware I have used V rather than delta V to denote the potential difference in these diagrams. This is just a little more convenient to write, as when talking about electrical circuits, we usually only consider potential differences rather than the electrical potential. But do keep this in mind. Anyway, the change in potential energy is this for one electron. Now, if you recall from lecture 4, the work done by the field, or in this case, the work done by the battery, is simply minus the change in electrical potential energy. So for one electron, this would just be E times V. This is the work done by the battery on the electron to move it from the negative terminal to the positive. Now, as we know, there are a lot of electrons in our system, so this isn't particularly useful on its own. If you recall, the electric current is the amount of charge delta Q moving through a point over a period of time delta T. If we rearrange this, we get delta Q equals I times delta T. The total work done by the battery on this quantity of charge, delta Q, is simply delta Q times V. But we can also write this as I times V times delta T. I times V times delta T is the amount of work done by the battery on the entire circuit over a period of time, delta T. This is a pretty neat formula. To be clear, this is the amount of energy expended by the battery over a period of time, delta T. V is fixed, and I varies depending on what's in the circuit. If you have these, you have the energy. Now, another useful quantity is the amount of energy expended per unit time. In other words, how much energy the battery expends per second. This is simply the work done divided by delta T, which using our formula leaves I times V. This quantity, the rate of work done per unit time, is also known as the power. We denote power with the letter P, equivalent to the work done per unit time. And for an electrical circuit, it's just V times I. Its units are joules per second using the first formula, but also volt amps for our circuit. So yes, joules per second is equivalent to volt amps. If you don't believe me, if you recall from lecture 4 and 5, volts are joules per coulomb, and amps are coulombs per second. The coulomb units cancel out to leave joules per second. We also introduced a new unit for power, known as watts, denoted with a capital W, named after James Watt, a Scottish physicist who pretty much caused the Industrial Revolution with his version of the steam engine. But this was a few decades before electricity was invented. Anyway, by calculating the power, we can figure out how much energy is expended by our battery over any period of time. But where is the energy going exactly? Sure, the electrons have it, and spend it as they move through the circuit. But what are they spending it on? As we recall, as the electrons move through our circuit, they are constantly bumping into nuclei and scattering. In other words, they experience electrical resistance, and this slows them down. The electrons are simply expending energy to move through all of this. Now, as you could imagine, the energy expended to move through a higher resistance part of the circuit is probably going to be larger than other parts. Let's add a few more resistors to our circuit to make it a little more interesting. As we saw in the last lecture, For a simple series circuit like this one, the voltage is equal to the current times the total resistance. As the total resistance is just the sum of all the resistances, we can say that V equals I times the resistance of the resistors, plus all the wires, plus the internal resistance of the battery. Before continuing, I should quickly talk about the internal resistance of the battery. Now, internal resistance is often ignored, as it's usually pretty small. We've been doing this so far in our calculations. But in the real world, it can make a big difference. Now, often on batteries, you'll see a voltage reading like 3 volts. However, this is actually the voltage when no current flows. This number is actually something known as the electromotive force, which is technically denoted by a capital epsilon symbol. This is not necessarily the voltage applied to the circuit. As the total electromotive force, or EMF for short, is equal to I times R total, which we can expand like so, we get some loss due to the internal resistance. Rearranging this, we get the EMF minus I times R internal equals I times the resistances in the circuit itself. So the voltage applied to the circuit is actually the EMF minus I times R internal. Now obviously, if R internal is way smaller than the circuit resistances, the losses will be very small. But if not, and the current increases, the voltage loss to the battery increases. So actually, batteries are lying to you, and the voltage, and therefore power output, that the circuit experiences can vary. In this case, to keep things simple, we're going to ignore the effects of internal resistance and say that the power generated by the battery EMF is completely supplied to the circuit. But it's worth keeping this in mind. Anyway, I went through all that to basically say that the power supplied by the battery is not fully supplied to the circuit, but we're going to pretend it is for simplicity. So we'll cross out the internal resistance, and obviously our wires are going to have very low resistance also, so we'll just say that they are negligible and focus on the 3 large resistors. So V equals I times R1 plus R2 plus R3. Expanded, this is V equals IR1 plus IR2 plus IR3. Now as we know, the power of the battery is simply I times V. Multiplying both sides of our equation by I, we get IV equals I squared R1 plus I squared R2 plus I squared R3. This is equal to the total power, and we can say that the total power is expended through each resistor. We can define the power expended by each resistor as simply I squared times R. In this circuit, the power expended by R1, which we'll denote as P1, is just I squared R1. We can write P2 and P3 for R2 and R3 as well. Just remember that the power provided by the battery to the circuit must be fully expended by the circuit. Always. Energy cannot be created or destroyed, so if it is being provided by the battery, it has to go somewhere. An interesting property of this circuit is that if we are to vary the resistances, we'll find that the power supplied to each resistor varies, even if the resistances stayed the same. This is because, if one resistance changes, the current must change, and the power through each resistor depends on the current squared. This can be quite fun to experiment with. As we know the power expended by each resistor, we can also easily find the energy used by each resistor over a period of time delta t, by multiplying our power values by delta t. If we time our circuit for a few seconds, we can see how much energy has been expended by each resistor. It really is very simple. Now you might also wonder where this energy actually goes. As we know, it is expended by the electrons colliding with the nuclei as they move through the resistor. But this energy can go to all sorts of interesting places. In a basic resistor, the energy is just converted to heat. Due to the collisions, the nuclei also vibrate a little themselves, due to the energy transferred from the electrons. The resistors therefore heat up, and the energy is released into the air around it, or spread along the circuit, which is also heating up to varying degrees. The higher the resistance, the greater the heating effect, for the same current. This being said, the power depends on I squared R. So yes, when there is a low fixed current, the power will be largest in the high resistance components. But if we have a really low resistance circuit, the current will be huge. As power depends on I squared, even if the resistance of a wire is very small, If I is huge, the power will be enormous. This is why short-circuiting is so dangerous. Essentially, when there is a huge current, even if R is small, the power is huge, so the amount of heat generated is huge, and the circuit overheats. Anyway, as we said earlier, resistors in a series circuit on their own aren't particularly useful, only for making sure the circuit doesn't overheat. Let's introduce another component, which you're probably all familiar with, known as the light bulb. On our circuit diagram, we denote this with a circle with a cross through it. Now you probably all know what a light bulb does. It releases light. But you may not have thought so much about how it works. A basic light bulb, also known as a filament light bulb, is simply a fancy material that when electrons flow through it, some of the energy is converted to light rather than just heat. The reason for this is a little complex and beyond the scope of this course, but basically, in some materials, when the ions vibrate, they release energy as light, rather than just as heat. So when we connect our battery to a light bulb, some of the energy expended by it goes into light, while some of it goes into heat. Now to be clear, the light bulb still acts like a resistor in our circuit in terms of the maths. So the total power expended by the bulb is simply I squared times the resistance of the light bulb. Now, when building circuits, we like to distinguish between the energy expended that is useful and the energy that isn't. We can say that our light bulb has an efficiency. The efficiency is the ratio of useful energy over the total energy expended. In other words, the useful energy divided by the useful energy plus the wasted energy. As energy used is just power times delta T, efficiency is just the useful power divided by the total power. If we say our efficiency of our light bulb is 0.8, that means that 80% of the total power expended by the bulb is being used for light, and the other 20% is used for heating. If the efficiency was worse, say only 40%, more of the power would be lost through heat. Over time, this can become very costly in terms of energy wasted. So let's now summarize this lecture. Electrical energy is the work done by moving charge through a potential difference. The work done by the battery on some charge delta Q is simply W equals delta Q times V. This is equal to I times V times delta T. Power is simply the rate of energy transfer, in other words the work done per second, W over delta T. A battery has a power output of P equals IV, and each resistor in a series circuit has a power usage of I squared R. Energy is dissipated as heat in resistors due to collisions between electrons and nuclei. Efficiency is the ratio of useful power output to total power output, or equivalently, the useful energy output over the total energy output over a fixed period of time. Real devices such as light bulbs convert electrical energy into light, but always have some waste as heat. So, after 7 lectures, we now have a good summary of how basic electrical circuits work, and how they might be useful to us. We understand how charges interact, how circuits are built, and how energy can be transferred from a battery into something useful, such as light. However, what we've learned so far is just the tip of the iceberg. There are so many more clever devices we can make using electrical circuits. In the next lecture, we're going to look at some more complex circuits. We'll see what happens when we draw circuits with multiple paths, and also come up with a key set of rules for calculating resistance, current, and power for any DC circuit. Specifically, we'll talk about Kirchhoff's laws, which neatly summarize all the equations we've come up with so far about circuits.